In this video, we're going to look at complex zeros of polynomials. And we'll start with an example that we've kind of already seen before. This would be a quadratic that is not factorable. So we could use completing the square or the quadratic formula, and we'll go ahead and use the quadratic formula to make our life easier. So let's go ahead and plug it in. So let's see, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. That's a sad looking c. Let me fix it. There we go. So for our problem, that would be 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 5 over 2 times 1. Okay, and what we're going to get is a square root under this denominator here. So that's going to be 4 minus 20, right? Negative 2 squared is 4. 4 times 1 times 5 is 20. So 4 minus 20 is negative 16 over 2. But now we can take the square root of a negative number. We'll use an imaginary number. So that's going to be, well, the square root of negative 1 is I, but the square root of 16 is 4. So that's going to give me 4i over 2. I'll go ahead and break that up and divide both terms by 2. And that leaves me with 1 plus or minus 2i. So that's how we would find the zeros, and they happen to be complex. If you were to graph this parabola, what you'd see is that it's going to end up hovering above the x-axis. I'm just going to pretend that it looks like this. It's going to end up hovering above the x-axis, and that's why it doesn't have zeros that are real numbers. It doesn't touch the x-axis, but it does have zeros. They just happen to be complex numbers. So this leads us to the fundamental theorem of algebra. Fascinating that you've probably taken multiple algebra classes, and this is the first time you've seen this theorem. A non-constant polynomial with real or complex coefficients will have at least one real or complex zero. In other words, just because it doesn't touch the x-axis doesn't mean we can't have a complex answer to our polynomial when we try to find the zeros. So what that theorem proves is what's called existence, meaning we know that there is a solution out there, but they don't really find an algorithm. What we do have is what's called the complex factorization theorem. Now, I don't want you to get too worked up on this theorem. As you can kind of see, I'm just kind of putting them out there. I'm not even filling in all the information because I don't want to get hung up on them. The ideas are actually a lot simpler than they seem. What the complex factorization theorem says is that if we manage to find the zeros, like we just did in that example, they called them Z1, Z2, Z blah, 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 all the way down to ZK with different multiplicities. That means we can set up the function in factored form. That's all, with the complex coefficients or the complex zeros. So we can write the factored form. It's just not going to look as pretty as it might when we're working with real zeros or nice whole number zeros or even fraction zeros. Okay, so here, let's look at an example and we'll go through the steps of how to find all the zeros. Now, just like before, we can start by listing all the zero possibilities, which I'm going to take a second to do. But then we're going to look at the graph and use the graph to help us actually test which zeros would be the most reasonable to start with. Okay, so looking at the last coefficient, which we called P, right? And that would be the 1 over here. The factors of 1 are only 1. And for the first term, Q, that's looking at the 12, the first coefficient. The factors of 12 are 1, 2 goes into 12, 3 goes into 12, 4 goes into 12, 6 goes into 12, and 12 goes into 12, leaving us basically with 1 over all of these combinations. So P over Q, the possibilities are 1 over 1, which is just 1. 1 over 2, 1 over 3, 1 over 4, 1 over 6, and 1 over 12. So basically all our possibilities are fractional. with the exception of the first one. And here, I'm not going to write it as 1 over 1. I'll take a second and go ahead and change that back to just being a 1. Here, let me kind of give a little bit of space here. There we go. So there's our possible factors. So now let's go ahead and grab this on Desmos and see what this looks like. Go ahead and share that screen and attach my keyboard. And let's enter that. So it was f of x, x equals 12x to the 5th minus 20x to the 4th plus 19x cubed minus 6x squared. It's quite a meaty polynomial. Minus 2x plus 1. Boom, there we go. All right. Wow. Okay. So to me, the best candidates look like 1/2, right? It does look like it's right between 0 and 1. And I could probably hover over here to verify that that's the case. Boom, yes. And the other one looks like maybe a third. Yeah, I think it is negative a third. Sorry. Okay, so we have a starting point. Let me go ahead and go back, and I will use synthetic division then to find those two that I feel like are pretty obvious on the graph. And then we'll see what's left if we are able to do anything else with it. Okay, so first of all, the fact that, here, let me go ahead and separate this. The fact that it hit 1/2, it looked like it had a multiplicity, by the way, of 2. So I'm going to try 1/2 twice. Okay, so let me go ahead and set up the synthetic division. So 12, negative 20, 19, negative 6, negative 2, and 1. Okay, so drop in the first one. 12, okay, 12 times 1/2, we're just halving it, so that's 6. Adding those, negative 20 plus 6 is negative 14, times 1/2 is negative 7. Adding that to 19 is 12, times 1/2 is 6 again. Adding those is 0, times 1/2 is 0, with the negative 2. Negative 2 times 1/2 is negative 1, and that's 0. Cool, okay, so it worked. Now I'm going to do 1/2 again because it looked like it had a multiplicity of 2. So repeat. Ooh, kind of going to run out of space here. So let me go ahead and do that down here on the next page. I think I gave myself enough room to do it again. 15, 12, 0, negative 2. Okay, I would just continue if I were you. All right. So that's going to be 12 times 1/2 is 6, negative 8 times 1/2 is negative 4. That's positive 8 times 1/2 is 4. That's 4 times that is 2. And there we go. Okay. So 1/2 twice. Then it looked like negative 1/3. It pretty much Desmos when it said 0.33 repeating. It seems like that's what 1/3 is. So let's verify that. That'll be 12 divided by 3 this time, negative 3 really. That's going to be negative 4. And then that's going to be negative 12 divided by negative 3 is positive 4. And then that's going to be 12 divided by negative 3 is negative 4. And we get 0. Okay, so there we go. That is all of the zeros we saw. So we can probably assume that what's left, this 12x squared minus 12x plus 12, is probably going to be complex. Okay, now, before I put it into the quadratic formula, and I could put it in the quadratic formula just like it is, I could also factor out the 12, like right off the bat, and just put these numbers in the quadratic formula just because they're smaller and easier to work with. So let's do that. I'm going to go ahead and do that right over here in this space. So I'm going to ignore the 12. I'll put that at the end. So that's going to be x equals, okay, so negative b is positive 1 plus or minus the square root of negative 1 squared minus 4 times 1 all over 2 times 1. Okay, so under the radical, it looks like we're going to have negative 3, which is not a problem because I can pull out the negative as an I. And for right now, I'm going to put it in front of the radical because that's where we put numbers that we pull out, but I'm going to rearrange that in a second. So we'll break it up as 2 fractions. That's 1/2 plus or minus. And now I'm going to put radical 3 over 2i. I'm going to write it like that with the I behind it. Okay. And there would be our complex numbers. Now, they asked us to find all the real and complex zeros. So these would be the complex zeros. So here, let me go ahead and list them. So we had 1/2 with a multiplicity of 2. Then we had -1/3, and now we have 1/2 plus or minus the square root of 3 over 2i. And I just, if I have enough room, yes, I want to write out the factored form of the function. So what we had was x minus 1/2 squared, that's the multiplicity of 2, times x plus 1/3 times x, and now here's where it's not going to be so pretty. X, it's going to be plus 1/2 plus radical 3 over 2i. That's the positive one. And then, oh wait, I just realized it actually should be a minus. Sorry. So because we're subtracting this whole thing. Sorry. So we're actually going to have to distribute that negative on there. And then the other one is going to be x minus 1/2. I'm going to write it, and then I'll put the parenthesis around it in red, just like I did a second ago. Okay. And then technically also, I don't want to forget that we factored out a 12. So that's going to go in the very front. Okay. So really the final answer is 12 times x minus 1/2 squared times x plus 1/3. Okay. And then distributing that negative into boop there. And into the first term. So basically into both terms. Wow, I don't know why I did it like that. There, like that. Okay, distributing the negative into both the terms. It's going to look like x minus 1/2 minus radical 3 over 2i, and then x minus 1/2 plus radical 3 over 2i. So we end up still with the plus and minus. It just has the minus in front of the 1/2. And that would be the factored form of f of x. And that's what the factoring theorem was saying, is that we can write out the factors even if they're complex numbers. All right. So in the next video, we're going to talk more about rational functions. But for right now, go work on that homework on complex solutions.